So in this video, I'm just going to go over content from our lecture 1, where we talked about position, velocity, and acceleration versus time of a particle. And then we'll finish off with continuous and erratic motion and using graphical methods to solve for position, velocity, and acceleration of a particle. So first off, let's begin with a question. In dynamics, a particle is assumed to have blank. A, both translation and rotational motions. B, only a mass. C, a mass, but the size and shape cannot be neglected. And D, no mass or size or shape, it's just a point. Well, in dynamics, when we consider the motion of a particle is something that has mass, but its size is so small that we can consider it a point mass. So it only has translational motion and no rotation. So the correct answer here is B. A particle only has mass, it has no measurable shape or size, and so we can also write it only has translation. Only translation and no rotation. Good. So in this course, we'll be talking about dynamics, which is just a subset of the field of mechanics. In a previous course, you might have studied statics. Statics is the case where structures and objects aren't moving and they're in equilibrium, and we're solving for sum of forces is equal to 0. In dynamics, we have motion. So we have acceleration terms, and if we sum the forces, they no longer equal 0 anymore. We have to use Newton's law, F equals ma. So in statics, we have sum of the forces are equal to 0, whereas in dynamics, we have sum of the forces is equal to the mass times the acceleration. And we can write these in terms of vectors because forces and acceleration is a vector quantity. In dynamics, there's two branches. There's kinematics and kinetics. Kinematics is just concerned with the geometry of motion and the study of motion, and kinetic is concerns with the interaction of motion and forces that cause motion, or vice versa, motion that causes forces. So first off, in the very simple basic case, we can look at the motion of a particle just along a straight line linear path. So in this case here, we have our path is the s dimension or s axis, and we have a particle at some distance s from the origin, and we call this position. So this is the case for one dimension. So we would call our position is equal to s. And as a particle is moving, its position is going to change. And over some period of time, delta t, our position might change some delta s. And we would call our change in position delta s. So that delta s is basically if we were to measure a particle's displacement or position at one time and then measure its position at another time, and then we find the distance between those two positions, that would be our change in position, which we could also call our displacement. Finally, there's something else we can add to this. In between the time that the particle is moving, delta t, the particle might move backwards and forwards. We don't actually know what's happening to the particle between these two beginning and end points of the total displacement. So the distance traveled by the particle might be greater than the displacement over that same amount of time. So for example, if a particle starts at some point s, here's our origin. Let's say this is our s-axis. And let's say at time 1, the particle is here, and then it moves some distance, and maybe it comes back. at time 2. So at time 1, our position is S1. At time 2, our position is S2. So our delta S, our displacement, is just going to be S2 minus S1. But in this case, because the particle moved forward and then turned around and started coming back, its total distance traveled, which we'll call ST, is actually greater than our displacement. So the total distance traveled we will call S with a subscript T. And in this case, let's just highlight that in red. The total distance traveled would be this red line here. And we can see that a delta S is just this distance between the start and end points. So in this case, our total distance traveled is actually greater than our displacement. So let's just label this. Our ST and our delta S. So that's position. Next thing we can look at is something called velocity. So velocity can be measured in several different ways, but in general, a velocity is a rate of change of your position with respect to time. So we can write velocity is the rate of change of position with respect to time. So we can say that if we have a particle and it is displacing a delta S over some amount of time, we can say that the average velocity is the displacement over that period of time divided by the amount of time it took to displace that amount. So we define average velocity we'll call it V subscript AVG, and that is equal to delta S over delta T. So that is the displacement divided by the amount of time it took to displace that amount. If we wanted to consider the average speed, because the total distance traveled might be different than the actual displacement over that period of time, we can say that the average speed needs to consider the total distance traveled. So we'll call our average speed equal to the total distance traveled divided by delta T. And then lastly, sometimes it's not too useful to look at the velocity over a time range. We want to know the velocity at one instant in time. So how we can do this is we can calculate the instantaneous velocity. If we look at the average velocity, imagine now we're trying to solve for this where that delta T is very, very, very small. And if we set that delta T to approach 0, we can get the limit, which gives us a first derivative of our position with respect to time, and we call that instantaneous velocity. So our instantaneous velocity we'll just call V, and that is equal to the first derivative of our position S with respect to time. Next, we have acceleration. So much like velocity was the rate of change of position with respect to time, acceleration is the rate of change of velocity with respect to time. rate of change of velocity with respect to time. So in the very same process as with velocity, we can say the average acceleration of a particle we'll write this as our average is equal to delta V over delta T. So we have a velocity at some point V prime, and we have an initial velocity V. We can calculate the average acceleration over that time period where that particle moved from one position to the other, or changed velocities, and that would be our average velocity. And then if we take the limit as that delta t approaches 0, we can get our instantaneous velocity. Instantaneous velocity, which we'll just call A, and that is equal to the first derivative of our velocity with respect to time. And if we recognize that the velocity is the first derivative of our position with respect to time, we could also write our acceleration in terms of our position with respect to time, and that's equal to the second derivative of position with respect to time. So there's one more point about acceleration. If acceleration and velocity are in the same direction, which means that the direction of acceleration is the same direction that the particle is moving, so a particle is getting faster, we call that acceleration. So acceleration is when A and V are in the same direction. So this means that a particle with a positive acceleration would be getting faster. The opposite case is when acceleration is acting in the opposite direction of the velocity. So we could call this negative acceleration, although it's probably not best to use negative acceleration because velocity could also be negative, in which case you have acceleration and velocity both moving in the negative direction, and you have acceleration. So if the velocity and acceleration are pointing in different directions, then you have deceleration, which means that the particle is getting slower. Acceleration is working against the motion of the particle. So we'll define deceleration is when A and V are in opposite directions. Great. So that's it for this quick video. Next video, we'll just summarize this and we will do an example.